All right, we are now recording, I think. Yep. And I'm trying to get the okay. See, still 4 people. Okay, he's trying to get the book opened up properly. Got to go through quite a few pages here. Okay, we're going to page 22. Pretty slow process here. Getting closer. All right, here's where we're starting today, or at least I have. My paper was indicating we had finished 1.2 and starting 1.3. Is that what y'all remember? Okay, got to move your manual out of the way. He's always in the way here. And I'm going to close off. Don't know if Ryan's coming today or not, but I'm going to minimize this and we'll come back if y'all see him come in. Now the trouble with having, you can't see what I've got, but I've got your names up at the top because it's not blocking the book page. However, that's where it comes in that someone is trying to come in the room. It'll be at the top and that'll probably be underneath your names and stuff, so I may not see it. So if you get any sense that he's trying to get in, please let me know and I'll try to do that. All right. Any questions before we get started today? We're already recording. Any issues? If not, what we're looking at today is differential equations as mathematical models. And I hope you remember, I just had it in one of my courses this morning, Cal 2 or Cal 3-1, I don't remember which, that I think it was Cal 2, a derivative represents a change, a rate. Well, differential equations then are talking about situations in which some variable, usually an important variable, is changing either with time or with some other issue. So that's where differential equations make really great beneficial mathematical models, because they basically are talking about anything to do with change. So what in the world is a mathematical model? Is a mathematical description of a system or phenomenon is called a mathematical model. It's constructed with certain goals in mind. It may not fit everything exactly, but you are trying to model some behavior that's happening in nature. Okay? Construction of a mathematical model starts with basically identifying the variables that are responsible for changing the systems. Okay, this is probably a really dumb example here, but I'll try to do it. Let's just say my wife is a researcher at UAB. Okay, she studies mostly a variety of things, but mostly a viral infection that is especially bad on unborn children because the virus can cross the placenta and affect the child while it's still in utero. Sometimes it'll have no effect, sometimes it'll have delayed effects, sometimes it's very radical effects. So if she was trying to model something with her data, some piece of information like the month of the year when the child was conceived, that has nothing to do with whether the child's going to get the disease or not. Okay, so therefore that would be, you wouldn't identify that as a variable. Is somebody coming in? I think probably so. Let's see. Yes, Ryan is trying to get in. I guess we'll let them in. Perfect attendance today, folks. Way to go. Okay. Way to go. All right. So I'll move this out of the way then, and we'll move on. So identification of variables that we're in chapter 1 still. Introduction to Differential Equations 1.3, Differential Equations as Mathematical Models. Okay, so identify the variables that are responsible for changing the system, that are affecting the system anyway. We may choose not to incorporate all those variables in the model at first. In this step, we're specifying the level of resolution of the model. Okay, now if you're just trying to get a ballpark thing, usually you try to limit the number of independent variables, because if you get too many out there, yeah, you may be able to model a system very precisely, but then you have all these variables you got to figure out the relationships from, and it may be very, very, very difficult to get those do. So you determine what level of resolution you want, and sort of limit the number of variables contributing. I know when I was doing my doctoral research, we could have modeled with really complex looking models, but man, they would have been a pain in the neck to work with in the next step. So we tried to keep the model as simple as possible, but still be very good, reasonably good resolution. Now, next we make a series of reasonable assumptions or hypotheses about the system we're trying to describe. Those assumptions will also include any empirical laws that may be applicable. Okay, so if, for instance, let's go back to the disease models, we'll see later that the sigmoid curve is a very appropriate type of a model to use for a disease, because it's been seen that diseases follow those curves very well. Okay, and especially in the light of COVID-19, when they talk about flattening the curve, whereas a sigmoid curve tends to go up pretty steep, anything you can do to flatten it keeps you from overwhelming your system, medical system, and hospital systems and stuff like that. So that's why they talked about flattening the curve. Okay, so let's move on. Here are basically, it's a reasonable little diagram, and you notice jump in any place. Okay, why not? Let's start here with assumptions and hypotheses. Okay, again, that's what we were talking about earlier. What assumptions are you making here? If you can make those assumptions, how is this thing changing? What are the variables that it changes with? How are they related? That is how you express those assumptions in terms of a differential equation. Does the disease depend on time? What does it depend on? Okay. Well, once you get those differential equations, then you've begun forming your mathematical model. Okay. Well, at that point, you might want to try solving these differential equations to see what your model is predicting that you're coming out with. You take these predictions, sometimes graph them or model them in other ways, check the model against the known facts. Are things balancing out pretty well or not? What if they're not? Then you might want to alter some of your assumptions, increase the resolution of your model, throw a few more variables into it, or get more data. That's always a good thing. So that may change your assumptions or hypotheses, then see if that changes your differential equations, and keep going around and around the circle. It seems to be pretty popular in some political circles to say, oh, but these scientists don't know what they're talking about. They were saying this one time and then that another time. What they're doing is adjusting the model. Exactly what we see here. You can't just out of the blue expect to hit on the perfect model the first time. Just doesn't happen, okay? Especially with a brand new disease you've never experienced before. So all these people that say, oh, but these scientists don't know what they're talking about, they changed their mind on this. Well, of course they did. Otherwise, it's not science. If you're not going all these steps, you're not following the scientific method, for instance. Okay, the mathematical model of a physical system will often involve the variable time. Okay, that's usually the rate that we're dealing with, the time rate. Solution of the model will then gives the state of the system. In other words, the value of the dependent variables, y or whatever, for appropriate values of time. That describes the system in the past, in the present, and in the future. That's where you check it against known facts. What happened in the past? Does your model seem to take care of that? What's happening now? Did the model predict this adequately? If both of those are yes, then you might feel a little more confident about saying, well, yes, this is likely what's going to happen in the future, depending on the time there. Let's take another, and this COVID has been compared to probably unfairly a lot to the flu. It's much different from the flu. It is a virus, that's true, but it's a different type of virus. It proceeds differently, so it's not a particularly good thing. But they still have flu seasons coming up every year, and what they model what disease, which strain of flu. There's several strains of flu out there, so they have to, about a year ahead, start planning for the next year, because you have to develop the vaccines, you have to go through all the processes and stuff. So what they do a lot is look at what's happening in Australia in their winter season, which is our summer season, and using that information to adjust our models and assumptions here for ours. And sometimes they hit it, sometimes they don't. Okay, they're getting better at being able to put together vaccines that cover a variety of features about the flu. So anyway, let's look at a few models here. And the very early one was that of population dynamics. One of the earliest attempts to model human population growth was by means of mathematics, was established by an English clergyman, but he was also an economist. A good combination, huh? His name was Thomas Malthus, very famous, both mathematician and economist, and probably somewhat as a clergyman as well. And if you think about those years, that was born just like a decade before the American Revolution. He was in Britain, of course, so he was probably 9 years old when it started, 12 maybe when it ended. But he did most of his work, this work particularly, right before the turn of the 19th century. Excuse me. Basically, the idea behind the Malthusian model is the assumption, here again the assumption, the rate at which the population of a country grows at a certain time is proportional to, and they highlight this here, proportional to the total population of the country at that time. Certainly a very small country with very dispersed population is probably going to grow at a very slow rate. But a very large country with lots of potential mating situations, people marrying and having kids and stuff like that, that population, that country is probably going to grow more rapidly. So that the rate at which the population of a country grows is proportional to the population of the country. What did we just say? Rate is a time rate. So dp, where p is the population, dt, where t is time, is proportional to, and that's what that little fish-looking symbol looks like, is proportional to the population itself. Now, how you go from a proportionality to an equation, introduce a constant of proportionality. One of the favorite of all times is K. Others will have others. So here is the differential equation that was basically Malthus's model. dp dt is equal to Kp. All right. Now, K is the constant of proportionality. And perhaps in different cultures, that constant may change, but the basic form is going to be pretty close to being met. Okay. Now, it fails to take into account factors that could influence human population growth or decline, immigration coming or going, disease, food supply, wars, those kind of things. Oh, those are anomalies. That would really mess up any model. But this was done, if you think about it, fairly early on, and especially for young populations, that would be probably a pretty good model. Okay? Now, many in the developing world, many of your populations are almost stable, if not decreasing. And there are a few reasons for that, and these were things that were not brought into the picture back then. A lot of modern couples are waiting longer to marry, okay, because they're trying to get their education in. They're trying to get a nest egg established before they marry, okay, and therefore before they start increasing the population. So those are some factors that would influence the rate of the population growth. Again, that probably affects the K, not the model. You know, the K can vary, okay. Other things, certain economic situations may make it so families choose to have fewer children than they used to. For instance, things like cost of education, cost of medical care, availability of, say contraceptives and things like this, that may be another, and that could definitely mess with the K here. So you see, but basically you still have that. Now here's the other thing, the aging population. If a good portion of your population is, say, over 60, which many developing countries that's happening, people over 60 aren't going to be reproducing. So basically, the longer people live, the less this model fits, unless of course you adjust your K. So again, most of this can be done by adjusting that K, the constant proportionality, without changing the model. Okay, but that's just one possible example of a differential equation being a model for population growth. Now, you'll probably find this very hard, bizarre to think about. Radioactive decay is very, very similar to population growth. Look at those two models. They're almost identical. Of course, the K may be very different. So let's look at radiation decay. Here we're talking about growth of a population. Here we're talking about decrease in radioactive material. The difference here, this is a positive K up here, this is a negative K down here. So this is contributing to a negative growth. The nucleus of an atom consists of a combination of protons and neutrons. Many of those combinations are unstable, and that is the atoms decay or transmute into atoms of different substances. Such nuclei are said to be radioactive. For example, over time, highly radioactive radium, which is radium-226, transmutes into a radioactive gas, radon, Rn-222. Now, a couple things to note. You probably don't have a periodic table in front of you. The 226 is the molecular weight of this radium. 222 is the molecular weight of that radon. Notice the difference is exactly 4. One radioactive particle that has a mass of 4 is an alpha particle. So this radium-226 has lost an alpha particle, that's the radioactive decay, when it became radon-222. Okay, and then you can model how rapidly or slowly or whatever that's happening. Now, radon gas is also radioactive, and it will decay to, I think it's plutonium or something. No, not plutonium. Goodness, I can't remember what, but something down chain from it. Okay, now what is the rate of that decay? If you started with a amount of radium-226, the rate at which it's decaying is proportional to the amount that you had. Okay, now basically this is the same deal that goes into making atomic bombs. Now that's not radioactive decay is associated with it, but the rate at which the reactions are occurring is proportional to the amount you have. Here's the deal. In a nuclear weapon, you have a certain mass, they call it the critical mass of your radioactive material. You keep them separate until it's time to explode the bomb. And at that time, you force them together, and then you exceed the critical mass, and this decay process goes really, really quickly. That's a nuclear explosion. Okay. Now, that's what happened in Hiroshima, Nagasaki. What they did, they had the bombs, and one of them was called Baby something another, Blue Baby or Baby Blue or something like that. I don't remember what they named them, but they had names, strange names for them. And it had that critical mass in there, but kept separate. And right at the time they wanted it to explode, they detonated conventional explosion that forced the two masses together very violently, actually. And when those two masses came together, then they, not immediate, but a very short order, had a nuclear explosion. And that's what the nuclear bombs were. Say again? Little Boy, that was it, not Baby Boy. Little Boy, okay? That's one of them. I don't remember the other one. They seem like they had a name for that as well. Now, what happens in a nuclear power plant, which we have in Alabama, they are controlling that radioactive decay process by keeping it constant. Not all of a sudden exploding, but keeping it at a constant rate. And they have what they call the tubes that they slide in and out of the reactors that they use to adjust and manipulate the rate at which their things are interacting. Okay. But this is talking about radioactive decay. Same thing holds. The difference here, radioactive decay is a negative number. Population growth, that K is typically a positive number. Okay. Same formulation. Pretty amazing. Those would be connected that way. A single differential equation can serve as a mathematical model for many different phenomena, like we just saw there. Very, very different phenomena. Population growth, nuclear radioactive decay. Okay? Now, here's another one. Now, this is slightly different model, but that incredible scientist, Isaac Newton, came up with this one. His empirical law of cooling and warming. Same deal, just one's going in one direction, one's the other. Again, the K could be positive or negative. What this is saying, now, capital T is temperature, little t is time. Too bad they start with the same letter. Keep it. Okay. The T sub M is the temperature of the surrounding medium, which I usually call the ambient temperature. Okay. So this is the change of temperature per time, that's what it is proportional to the difference in temperature of your material that you're looking at and the ambient temperature. So let's just say we took the turkey out of the oven. Okay, I'm thinking Thanksgiving already. Took the turkey out of the oven. Let's just say the temperature of the turkey was around, what do you want to say, 350 degrees, or would it be higher or lower, or something like that? Well, the room temperature is right around 70 degrees. Okay, so the rate at which that turkey is going to drop its temperature is going to be pretty high to begin with, because the difference in temperature is pretty great. But then once the turkey cools off some, the difference in temperature is not as great, so the rate decreases. Okay, so the change of temperature is proportional to the difference in the temperature of the object and the ambient, or temperature, they call it ambient temperature too, surrounding medium. Okay, now making that a equation, just take out the proportionality sign, put an equal K. Now that K goes outside the parentheses because it's that change of temperature that you're interested in, not the absolute temperature. Okay, how much is it? Now, if that were a snowbank, if you were living in an igloo when you took the turkey out of the oven, this is sort of dumb, then that rate would be much greater because the ambient temperature would be much less than this, so it would cool off much more quickly. Now here we go to the spread of a disease. Very appropriate one here. And they mentioned the flu virus also can be any disease, including COVID-19. Spread throughout a community of people coming into contact with other people. That's why we wear masks. That's why we keep the distance, 6-foot distance. We're trying to slow the rate. We're trying to level the curve. You're trying to control that K. Keep it as small as possible. Okay? Now, let X here be the note, and both your X and your Y are dependent on time. X is the number of people who have contracted the disease. Y is the number of people who have not yet been exposed. Now, it seems reasonable to assume the rate dx dt with which the disease spread, that's the number of people contracting the disease, that would be the rate of spread, dx dt, is proportional to two things: the number of encounters or interactions between the two groups. Now certainly if you had, my internet's unstable, so I'm going to quit talking about, okay, did I break up anything? Could you tell? This morning it said my internet was unstable. I had 5 bars when it said it. This afternoon, however, I'm down to 3 bars, so I can believe it better now. Okay. Now, if someone had already had the flu and someone else had the flu, guess what? Those two people get together, no chance, very little chance of anyone else getting the flu because of that, because they both already had it. Or two people that neither one of them had the flu, they can't pass it to each other. But if someone from the first group who has had the flu and is currently got the flu encounters someone who has not been exposed yet, that's when your interaction is going to happen. That's when the rates are going to increase. So here, your proportionality is the rate at which the number of flu cases is increasing is equal to your proportionality constant times the number who have it already times the number who haven't had it, contracted it yet. And if you think about this, when the number of known cases is very small, you're going to be on the flat part of the curve. And that's where we were basically probably January, February, and early March. We were down here very flat with COVID-19 because not that many people had contracted it, and it was therefore not spreading very rapidly. But sometime in mid to late March, the curve started moving upward. More people had it now. There were quite a few people who didn't have it, so that product there was going up as the number of people who were infected and had been infected is now encountering more and more people who had not. That's when the curve started going up. That's where we went into basically almost a lockdown. Okay? Every time we've relaxed it, okay, when we went into that, it stopped the curve growth and sort of leveled out a while. Then we relaxed it and here it goes again. And then we relax it and here it goes again. So that's why we've had such a roller coaster ride with the number of infections, because as soon as the numbers start going down, people are going to forget about masking, forget about this, go back to work, go back playing football, whatever. Yes. Did someone say something? Okay. What was funny? I couldn't understand. You're not hearing me well? Is that what you're saying? I can barely hear you. What did you say? Are you talking to somebody else or me? You can't understand much of what I'm saying. Is that what you're saying? Okay. 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 You're coming across to me very garbled too. It's going like, okay. Okay. Who is that? Jesus? Yeah. Okay. So it may be your connection, Ryan. I don't know. Um, the others, Jesus was here. Could you hear Jesus well when he just spoke? You could. Okay. I heard him clear as a bell, but I'm not coming across clear as a bell. Is that what you're saying? Okay. Yeah, you're coming across a little garbled to me too. That's why I'm having to ask you to repeat things. Okay. Now, let's continue with this model. Okay. Let's go back to COVID, So as long as we're controlling the number of interactions between the infected group and the non-infected group, we can keep the level fairly low. If we keep the levels or the rates fairly low, then we don't overwhelm the hospital system and the healthcare system. But if they were to take off and go up, man, we get swamped. And there was a time back, I think in midsummer, it was about 2 weeks after Memorial Day. Now my internet connection is unstable, so I'm not surprised if I'm a bit garbled then. Was I worse then than I am now? Okay, I can't hear. Okay. So anyway, there was a time in probably early June, mid-June, when the rates really started going up, and that's because everybody had relaxed around Memorial Day. People went to the beach, people did a variety of things like this, and wound up infecting a lot more people. UAB didn't get swamped, but boy, they were coming closer and closer and closer to saturating their care system. Some places across this state, I think Montgomery has some really tough times when they're just about every hospital in Montgomery was almost filled to the max of their units where they could handle COVID patients. Things have equilibrated, stabilized some now, but who knows, once they start all this football and other sports back, who knows, the numbers could blow up again. All right, now, let's suppose that we have a small community, fixed population of N people, not sort of a wide open deal. If one infected person is introduced into that community, so all of them are not exposed, then it could be argued that X and T are related by this relationship. X plus Y, the number of infected, plus the number not infected, is equal to the original number in their population plus 1. Why? Because you introduced one more person in who was infected. And using that last equation to eliminate y, which was the number of people not infected up here, then you get a function of x and x alone. See, here you had x and y over here, but only x here. So dx dt is equal to kx times n plus 1 minus x. Rather strange, but that's how it worked out. And that, the obvious initial condition was that at x equals 0, you had one case. When time was t equals 0, you had one infected case. So that gives you this curve they call a sigmoid curve. And the sigmoid curve typically starts flat and then starts increasing. Sometimes can get very big increase, other times it's sort of flat, but at some point then it starts flattening out again. Why? Almost everybody's been infected. So if everybody's been infected, there's lower case of people getting the disease. And that's what they call, and you probably heard people talk about it, herd immunity. That you've gotten to the place where your rates are going to start going down just because a certain saturation, close to saturation, has occurred. And usually that's around 60 to 70% or 70 to 80%. When that happens, then the rates start going down. Of course, by that time, you've had an awful lot of sick people, very, very sick. And one thing about COVID, we can't tell if some of the damage that's done by COVID is all repairable or not, okay? Because people start getting very short of breath. I was talking with one of the staff members at the college early on. His son came home from college, tested positive. He infected his whole family, pretty much. I think one sister managed not to get infected, okay? So the staff member said that, boy, he couldn't keep food down. I mean, he lost like 25 pounds. He had trouble breathing, all the classical type things. When he got better, he said still he's completely free. He's back on campus, but he said, I can't do too much without feeling like I've lost my breath. The doctors told him it could be a year that that's happening, okay? Now, the question is, will it get better in a year, or is that actually a permanent result of COVID? We don't know the answers to that yet because it hasn't been around a year yet. So they're still finding information. So that's why keep that curve as flat as possible. Do the mask, do the social distancing. Don't get around people if you can't help it. My wife just this morning, if she needs to go to the grocery store, she tries to get there when the store first opens, because then she thinks the fewest number of people will be in the store except for the workers. They are all masked, guaranteed to be masked. They're taken care of. They're not coming to work sick. So the likelihood of her being exposed to something is less, okay? Or she goes to a place where they put the order in her car. She doesn't even have to interact with anyone. She did that today too at Sam's. She went this morning to Publix, then she went this later in the morning to Sam's, and because they messed up something at the order of Sam's, she had to go into the store, and she said it drove her nuts, except she stayed away from people. So she was a little worried about it, but not. The reason she's worried, we're going to be around her folks on this coming weekend. Oh, and by the way, I forgot to tell my first two classes this. Y'all probably weren't aware of that, but let me give you the good news, bad news situation. First, the good news. Monday is a holiday. Labor Day, right? Yeah. School is closed. State system's closed. Everything's closed on Monday. The bad news is that means we won't be meeting on Monday. Sorry about that, but get over it. Okay. So But what I was going to say to do with that, her folks are so anxious. They're in the 80s. They're so anxious to get out of the house. They're going to drive to a place they have at Smith Lake and wanted us to come too. So Karen was really concerned that she had been exposed to a few more people that she didn't want to be exposed to this morning because she was going to be around her folks this weekend. So she's just hoping that by masking and trying to keep social distancing, she didn't pick up anything because she's going to be around her mid-80s parents this weekend. All right, let's move on. Chemical reactions are other places where differential equations are used to model these reactions. Now, another little twist here, there's a couple of different kinds of reactions. The first of these, the disintegration of a radioactive substance governed by a differential equation that we talked about before, said to be a first order reaction. Something's happening and the numbers are going down. In chemistry, a few reactions follow that same empirical law. If the molecules of a substance A decompose into smaller molecules, it's a natural assumption that the rate at which the decomposition occurs is proportional to the amount of the first substance that was there to start it. And as the more and more stuff has decomposed, then the rate will slow down. Okay. Now, here in chemistry is how you express that. If x of t is the amount of substance A remaining at any time t, then the rate at which it's decomposing is oops, my internet connection's unstable, so I'll quit talking about. Okay, I'll get back to differential equations. Did I break up a little there or not? Don't know. Okay, so dx dt is equal to kt. That's just like radioactive decay. K is a negative constant since the x is decreasing. And here's an example of that. You don't need to know the chemistry of it, but what the assumption here is, this is the thing that's decomposing. It's decomposing to this. We're assuming you got plenty of this and plenty of that always. So basically, this is decomposing to form that. Okay? Now, first order reaction. On the other hand, what if you had another situation that dx dt was equal to k times an alpha minus x times a beta minus x? Here, the alpha and beta are amounts of two chemicals, A and B, in initial amounts. Then the instantaneous amounts are not converted to chemical C. That would be A minus x, alpha minus x, and beta minus x. Therefore, the rate would be dependent on what's left that hasn't been converted. So this is a second order reaction because it doesn't involve just one material. You have two materials. One's converting, one's getting bigger, while the other's getting smaller. That one gets smaller, this one gets bigger. That's a second order reaction. So that differential equation will be more complicated, like this. Okay? And so there's a couple of illustrations from chemistry. Now, mixtures. Mixtures are change of one material per change of another. Here we have an input rate, the material coming into the system. We have the mixing rate, so what's in the system is changing in here, and then you have an outflow. Now in this case, the inflow and the outflow are the same. So the total in the tank is a constant, 300 gallons. But the amount of the material for this is the brine coming in is a stronger brine than that that's going out. So therefore the quantity in the tank is actually increasing in salinity. And these models can get slightly more complicated. So the change of the amount of, say, salt in this brine solution, dA dt, how much is the salt changing in the tank, is equal to the input rate of salt, which is coming in here, minus the output rate of salt, which is coming out. So that's the amount of salt. But then you have to figure out, well, how much salt is there? Well, the input rate, that's going to be a constant, always the same amount coming in. The output rate, though, is not always constant. It started with whatever your initial value was and then has been going up ever since. So this is not a constant, this is a constant. So they go through, they give you numbers and show you how these work. Whoops, hit the wrong key. All right. This would be then the differential equation. You see, it's a little more complicated. The net rate at which the amount in the tank is what's coming into the tank minus what's going out. Okay, what's coming in is a constant 6 pounds per gallon. What's going out is A over 100 pounds per gallon. So that then is the rate at which it's changing. And this is the amount that's in there at any given time. So you see the differential equations can take on a whole lot of different forms. Okay. Now, they say something here which is sort of important. Don't confuse R in and R out. That's just the rate at which the fluid is coming in and out. That's not the amount of salt going in and out. The Rn is proportional to how much salt is coming in. That's why it's a 6 there. But the R out, because your amount in solution is always increasing, so this is a variable going out, but the rate at which it's going out is the same. So the Rn and R out are the rate of solutions, not rate of salt. Now, sort of a different take on that is what if you don't have stuff coming in, but you're trying to drain a tank. And that follows what we call Torricelli's law. By the way, some of these are paper topics. Isaac Newton was mentioned, Torricelli's mentioned. You may have seen other names or things in here. Law of heat. I mean, there's just lots of things you could choose to write on if you're just looking at this section here. You don't have to, okay? But anyway, there's a lot that goes into calculating this. Ultimately, your equation is dV dt is equal to minus A sub h, where A sub h is the area of the hole in square feet, which is a pretty big unit for that area, times the square root of 2gh. Now, that's the rate, the volume of water in the tank. If you also are dealing with, say, the salts or other things in the tank, or no, I'm sorry, the rate at which the tank is, the water is going down in the tank, that would be proportional to the amount that's in the tank and the area, if it's a cylindrical tank. So you see, you can measure change of volume, change of height. It's just whatever your constant is that you're looking at, whatever the measurable thing that you're doing. If you're looking at whatever they call the tubes over here, the rate at which that's going down, that's the change of height. If you're talking about the volume, how much is in there, that's the change of dV dt. All right. And they are connected by a fairly simple formula. Now here's one that, whoa. Are any of you still in physics, or some of you? Some of you are, aren't you? What's that? What course is that? Physics 218? Yeah, modern physics. They have it listed wrong. That's going to be Dr. Bryant. And the reason, I don't know why they listed it wrong. I want to say they're dingbats, but I shouldn't say that. Um, they had the course listed as being on the Birmingham West campus. I said, we're not going to be on campus. This is going to be virtual. And then they said, well, we're not sure that Dr. Bryant is qualified, is credentialed, or whatever it is, checked off to do online classes. I said, not online classes, virtual classes. So their objections and everything else. But the reason I know I'm not teaching it, the time they put it in there for was a time that he could teach it. I'm teaching a physical science class at that time, so I can't possibly be teaching that class as well. So that's going to be Dr. Bryant, if it makes. That's the problem, the if it makes. Okay, hopefully it will. But are any of you taking Physics 214 this term? Anybody? Well, if you've already had it, you may recognize this. This is what we call an LRC circuit. It has an inductor in it, it has a resistance in it, and it has a capacitor in it. Okay, now I don't know what makes those noises. I've never figured it out. I don't think anyone else is coming into class. Let me just check. We have lost somebody. Is anyone trying to come back? Okay. Looks like we lost. Who was it? Oh, Jemanuel. We lost Jemanuel, it looks like. Maybe that's what we had. He had to leave or got disconnected or something. So if he's trying to come back, if y'all can sense that, let me know. Now, here's the thing. These are, by the way, not direct currents. They're alternating currents. So your E is not a fixed number. If the current is alternating, that means the voltage is alternating. Sort of a sinusoidal curve. Okay? So this is a alternating current because L and C don't work on direct currents. They only work on alternating currents. So I know this has to be alternating current. Well, this is a variable alternating current depending on time. Your L is a retarding the change. I think I've said it right. R is in real time with the change, and C, maybe L is leading it and C is lagging it one way or another, but every one of those stands for a differential. You can represent it with a derivative or a differential equation. So you probably did in Physics 214 Kirchhoff's laws. Now I had two laws. One of them was called the loop law, and the other, the first one was called the junction law, and the second was called the loop law. This is talking about the loop law. On a given loop, then the loop law has to fit. And the inductance relates to the change of current, but current relates to change of charge. So if you wrote L di dt, that could be written as L second derivative of charge with respect to time. I times R is just I times R, except I is change of current with respect to time. Capacitor, on the other hand, relates only to the charge. So this would then be a first order equation. This would be a this is zero order equation, first order equation, second order equation. Okay? Excuse me. Goodness gracious. My eyes are drying out like crazy. All right, let me get a sip of something here. My throat is drying out too. All right, so now we can express your equation that you see going around the loop here, because this is how it's affecting voltage. Okay, so the inductor is L di dt, which is L d2q dt squared, plus R times dq dt, plus 1 over c q is equal to E of t. All of these are functions of time. Even the charge is. They don't put it there, but it is. You know it is, because here you're taking derivative with respect to time. Here you take a second derivative with respect to time. So the charge, Q, is a function of time, and that equals those added together, or if some of them are negative, subtract, or whatever, gives you the EMF, or the voltage as a function of time. So there's a pretty classic example of a mathematical model that really fits like a glove. Okay, now before we move on to the next one, I just want to mention one that's really important. I don't know if you remember from your physics, especially 214, that electric fields do something like this. Magnetic fields do something like this, and they're related to each other. The electric field doing one way, the magnetic field going another way. They influence one another, and that's what creates electromagnetic radiation, which is what's transmitting this to you, electronic transmission. It's what's sending gamma rays or other electromagnetic radioactivity through space. I mean, it's all over the place. Now, when they were first discovering that electricity influences magnetism, magnetism influences electricity, a very famous, very brilliant Scottish physicist named James Clerk Maxwell. Now, it's spelled like it's C-L-E-R-K. It looks like it's Clerk Maxwell. It's actually James Clerk Maxwell. Came up with a mathematical model describing what he thought was happening. The thing is, though, he was probably 70 years ahead of his time. They didn't have the technology at the time to determine whether his mathematical model, and it was in partial derivative, so we're not getting into that. You won't see it in this book. But that partial differential equation described exactly what was going on, or at least he thought it would, in electromagnetic theory. Finally, about, like I said, a generation or longer later, along came Heinrich Hertz, that they named the symbol for frequency after. And by the time he came along, the technology had advanced to the point where you could measure that. And when he measured it, it fit to a T. So James Clerk Maxwell came up with a mathematical model that no one could even test. So he couldn't go close the loop on his, because his mathematical equations, his differential equations, fit like a glove. Okay, so since we're talking about electrical, I thought I'd throw that one in. Now we move back to Isaac Newton. He's all over the place here. Falling bodies. Now, actually, before him was Galileo, and we're going the Leaning Tower of Pisa, that features him. But in both cases, Galileo came up with the idea. Some of these ideas, Newton perfected them and put the mathematics to them. And here's Newton's second law. My internet connection, it says, is unstable. I'm up to 4 bars now. Okay, did I break up some then? No? Okay. Well, I can't ever tell, so I quit talking about math when it happens, so we can do. So here is basically Newton's second law. Force, which is mass times acceleration, is equal to mass times acceleration, you might say. This is the mass times the acceleration of an object that's falling is equal to, and they put a minus sign here because it's going downward, the mass times the acceleration due to gravity. Okay, and that's it. You can divide out the masses, and there's your simplest form of Newton's second law, that the change of the speed of an object, that's displacement of an object, is equal to minus g. That's what's pulling it downward. Okay. Now, you probably ran into that in Physics 1. And this was technically Galileo's experiment. He dropped the rock off the top of the Leaning Tower of Pisa, and timed the fall, and sure enough found out this formula made sense. Okay. But Newton formalized that in the three laws of motion. That just dealt with one. Okay, let's move on down to, well, I can't get it to move. There we go. All right, here is that equation here, differential equation with initial values. Okay, initial displacement of the object we'll call as S0. That could be how high it was here. The rock dropped off the top of the Leaning Tower of Pisa, and its velocity at that time was the initial velocity. Now let's just go back and look at this and see if that's kind of making sense. When they show this, it shows the ball is thrown upward, then comes down and falls. That has an initial velocity. If it was dropped off the Leaning Tower of Pisa, it would have been initial velocity be 0, then it just goes down. It wouldn't have any upward motion. Okay, this formula works for both. Okay, now from elementary physics, hopefully you are familiar with this equation too, that 1/2 negative 1/2 gt squared, that's the acceleration due to gravity, plus vt, that's initial velocity, plus initial displacement, that is your displacement at any time t. Now that's a simple formulation for things like this. There are some simplistic assumptions here that aren't always met. And here's what some of those assumptions would be. One is you assume that the velocities are so low you don't have much air resistance. But what if they're not? Well, before the famous experiment by Italian mathematician and physicist Galilei, okay, I guess is how you say his name. It almost sounds like something they'd sing in the Sound of Music. He amazingly died, I think, the same year that Newton was born. Let's see if they give Newton's dates in here somewhere. We first talked about Newton back here. No, I don't see they mention them. Okay, sorry about that. I was thinking that they gave his dates, but I think Newton was born, I believe, on December 25th, Christmas Day, the same year that, oh, there it is. He was born in 1643. Okay, now, the reason there is a discrepancy here is that they changed the calendars right around this time. I don't know if you remember hearing about the Gregorian calendar as opposed to whatever the one before that was. When they changed the calendar, that moved his birthday into 43 rather than 42. But originally it was thought that he was born on Christmas Day in 42, which is the same year that Galileo died. Okay, but when they revised that, he was early January. So it's almost the same. Within a year, within the same year of Galileo's death, Newton was born. And Newton just, even though he was a baby then, by the time he got to, I guess, age of accountability, when he was, thinking on his own and stuff like this, he read a lot of Galileo and picked up right where Galileo left off and moved on from there. So here was Galileo. He mentioned that it was generally believed that heavier objects in free fall, such as a cannonball, fell with a greater acceleration than lighter objects. But I swear in my throat. Let me see if water will help. He proposed all objects fall at the same rate. The difference being, though, lighter objects are more apt to be influenced by resistance or friction. Now, of course, that makes sense. So here is then the better, more rigorous definition. You have gravity pulling downward, but air resistance resisting that fall. So at some point, as the velocity keeps picking up, but you see, this is almost like Newton's law of cooling here, or warming, that is the difference here. Okay, when the velocity is very small, this is incredibly small. The air resistance is small. So gravity has most of the play here. But as this picks up in speed, then the velocity increases, so the air resistance becomes more. And or at least when I was a boy child, I remember doing this. We never had a car with air conditioning until way, way late in my childhood. Probably I was already past childhood then. So we always, in the summer or any warm time of year, had the windows down. And I liked to, when we were going, it was dangerous, it was stupid, and all like this, but I loved sticking my hand out the window and feeling the wind pull me back. Okay? Why? Well, if you're going real slowly, you put your hand out the window, you may feel a little bit. But if you're going at a high rate of speed, it can almost pop your arm out of joint. Okay? You didn't want that to happen. Okay. Now, why? Because the greater air resistance at greater velocity. Very slow speeds, very little air resistance. Gravity wins because gravity is constant. Okay? But at the higher speeds, then this gets more and more air resistance. At some point, the air resistance equals the fall, and at that point you call it terminal velocity. So an object will stop accelerating and start falling more slowly. That's what the ancients said. That's what they observed, that if you have a very lightweight object, you reach that equilibrium point much faster. So that's why they said lightweight objects fall at a slower rate than heavy objects, because they were only looking at terminal velocity. And certainly the terminal velocity with a larger mass here is going to have to achieve a larger speed for that terminal velocity to be reached, whereas a very low mass object like a piece of paper or something like that is going to fall at, this is going to be a very small number. You'll reach that terminal velocity much, much sooner. Okay, now that process there is called viscous damping. So your net force acting on something is your acceleration due to gravity downward and the air resistance resisting that increase downward. And there's your formula there, because acceleration is dv dt. And since this has velocity in it, that has velocity in it. However, if you wanted to make it dependent on displacement, Come down to the next set of equations, because velocity is ds dt, so this becomes dm times d2s dt squared, second derivative of displacement with respect to time, and that's equal to mg minus k times ds dt, because that's what velocity is, ds dt. Or you can add this to both sides and you get this one, that the change of displacement with respect to time, mass times that, the second derivative of the displacement with respect to time, plus the whatever your constant is there, times the change of displacement with respect to time, which is velocity. Now my internet connection is unstable. I'll quit talking math. Okay. Did I break up some there? I don't know. I've got 5 bars. I see no reason for the say again? Did I break up? I did. Okay. I don't know why, because I had 5 bars of internet, so I don't know why it did. So anyway, that's just 2 different ways of writing that same differential equation. Very common thing. Now these get to be a little weirder, okay? More complicated differential equations. Have you ever noticed that when the line, I'm looking right now at the line that goes from the power pole out in the alley to our house right over here, that always has a sag in it. Why didn't they put it tight? Weren't they just wasting wire? Guess what? You have to have a sag in it, okay? You cannot possibly, because gravity is always pulling down on it. Even if you tension it as much as possible, the metal would still sag a little bit. Now, the issue with that is, if you put that up, say, in the middle of the summer and put it as tight as you could, and had a minimum sag in it, then that winter, when the line contracts because of it's the reverse. Yes. Is it time? Oh my goodness, it is, isn't it? Yeah, thanks for telling me. Anyway, we'll pick up with suspended cables next time. I'm probably spending too much time in this, but I'm just trying to show you different examples of differential equations and how they are used in all sorts of fields. And since most of you, I think, are going to be in engineering fields, they're all over the place in engineering. So what we're doing now is suspended cables. That's where we'll begin next time. We almost finished 1.3. Now I want to ask y'all a question. Okay, since this is the last section in the chapter and none of your test questions are going to be really on this section, do you want me to go on and put the first test out there for you so you can use the long weekend to start working on it? Yay? Okay, so I will do that sometime after class gets over with, which is going to be pretty soon. Soon as I can get that done, I will put your first test out there. Now I'll tell you ahead of time, this test is not trivial. There's a lot of verifying differential equations that this is a solution, and some of them got way hairier than I ever wanted them to be. I was using examples they had in the the author had put out there, and I thought they were basically of the same magnitude of, say, homework exercises. Boy, he put some doozies out there, and I didn't realize it until after I'd already put the test together. So take your time, work through them, show your work. I'll give as much partial credit as possible. They're really easy to get bogged down. None of the stuff we're doing right now is going to be on there, so don't sweat that. All of this is in section 1.1, 1.2, but it's at a pretty hefty level. So get working on these as soon as you can. We'll be a while in chapter 2, so you have plenty of time to do this. Technically, it's supposed to be a week. take the time you need, but don't drag it out too long, okay? So I'll put out that test. It'll be under Blackboard Message. That's where I'll put your test, under Blackboard Message, okay? Any questions? Okay, let me just give you some... Say that again. What was the question? Okay. Homework exercises here, if you want to look at any of these, either 1 or 3, population dynamics. 5 is Newton's law of cooling and warming. 7, spread of disease or technology. That's interesting. Virus is a disease or in technology, either one. Mixtures, either 9 or 11. All these should have answers in the back. Draining a tank, Torricelli's law, that would be number 13. Series circuits, that's number 15. Falling bodies and air resistance, that's the one we were just looking at. That was number 17. Now we didn't do, yeah, we did. Number 19 is Newton's second law. We didn't do one like 19, which is, it's also Newton's second law, but that's Hooke's law then. So you can probably do that with no problem. 21 is Newton's second law with variable masses. That would be like rocketry. So that one you should be able to, if you want to look at it, you can. And then Newton's second law and the universal law of gravitation, that's number 23. Stop right there, and I think we'll just pick up from there. There's not many left, but we'll look at those next time. All right, any questions, issues, concern? Yes? His name is Dennis G. Zill. Z-I-L-L. Dennis Z. Zill. Z-I-L-L. Okay. Say that one more time. If you are on Cengage Unlimited already, yeah, you get it. I mean, it's part of the deal. It's a Cengage book. So if you're on Cengage Unlimited, you should be able to access it right immediately. Are any of you not on Cengage Unlimited this term? You're not. Okay, do you want me to send you this PDF of the book? Okay, I'll just put that out there on Blackboard Message as well. A student this summer gave it to me, and she said, well, Auburn said that, you know, they can share books like this, so if it's only for educational purposes, so I don't mind sharing too. So it was given to me, I'll give it to you. I'll put it out there for any of you to use that want to. Okay? That's exactly what you see on the screen. Okay? So I'll put the test out there, I'll put the textbook out there as well. Blackboard Message. Okay? Any other questions? Okay, I'm sick and tired of sharing, so I'm going to stop share right now. And that's gone away. If there are no further questions, I'll end the meeting. None? All right, well, take care. Have a good weekend. And of course, working on differential equations will make it a good weekend. And we'll see you on Wednesday, not Monday. Okay, take care. Bye-bye.